right, so since we want to use the fundamental theorem part 2, and that means we need antiderivatives, then we better know how to do antiderivatives. Now, what I want to talk about right now is why do we use the integral sign with nothing on it to mean antiderivative? And I'll be honest, when I was in your shoes, sitting in high school, our book, and my teacher was a great teacher, but I never did understand. I always thought integral and antiderivative were the same thing. When I thought of integral, I thought of antiderivative. I thought they were the same thing. Not till later did I come to realize and learn that they're not the same thing. The antiderivative is just one way of finding a definite integral, right? But an indefinite integral and an antiderivative are the same thing, right? An indefinite integral and an antiderivative, that is the same thing. Now, where does this come from? So here's what I want to show you. Again, I don't care if you write this down. Don't really need it. So here are the different integrals we've looked at so far. Now, this one is what? What do we call this one? Definite integral. So how do we work this one? 1/3 x cubed, right bracket, 3 to 4, put a 4 in there, that'd be 64 thirds. Put a 3 in there, that'd be 27 thirds, right? Which would equal, what, 37 thirds, right? It's just a number. It's a fixed piece of area. A definite integral is just a number, okay? That's all it is, okay? All right, now, this, though, is an area function, right? And we've got an x up here, so we've got to use t in here, right? But it's a related thing. So what would we do on this one? Come on, we just did it. We just did a couple in the quiz. I just erased it right here. You got a free initial condition, right? It's 1/3 x cubed plus c. You know that, I don't know, call it big F or something. Doesn't matter. Big F of 3 is 0. So this would be 1/3 times 27 plus c equals 0, right? So that's 9. So c would be -9. Would you agree? So this is 1/3 x cubed minus 9, right? It's a specific antiderivative. Right? It's one of the many antiderivatives, right? But we have a free initial condition because of the 3, so we can get it. Now, what about this one? One-third x cubed, and that's it, right? Because we don't know a left edge, right? And so this is what we call the general antiderivative. Now, so those are the different ones we work with. Here, if you know the left edge, you can figure out the c value, right? You get one of the antiderivatives. If you don't know the left, but look at this. We don't know the right edge because the right edge can move, so that's x. We don't know the left edge. So doesn't it make sense that if you don't know this and you don't know this, why even have them there? You get what I'm saying? Why even have them there? So that's why we just write the integral symbol, and then instead of having to use t's and we have to worry about that, we just say, okay, let's just do that. That means the general antiderivative. You see where we're coming from here now? So a definite integral is just a number. This is an area function. It's one of the antiderivatives, okay, with a specific c we can find. And then when we don't know either one of them, heck, let's just leave them off. And then that's just our general antiderivative. So that's called an indefinite. So this last one here, this is called an indefinite integral. So that's what we talked about the other day. Okay? And so we did this page, and we did this page, and we did this page, and we came up with this when we first did U substitution. We did that one. Did we do this one? I don't know that we did this one. Okay? So let's work some together. So let's go in your notes here. Now, I know you might have some questions on your homework. That's fine, but I'm going to go through this, and that may answer some of your questions on your homework. Okay, so let's do this problem right here. All right, So if you were looking at this problem, what would your thought process be? Could throw the 4 out in front for sure, yep. Could do that. I could do that later too, so. Pick something for you, right? I mean, you should always look at it and say, can I just do a regular antiderivative? I mean, for example, if this problem was, if I had 4x, and then this was just 1 plus x squared like this, and there was no square root, what would you do on this? You just distribute, right? So if I gave you this problem, you would just distribute that, and then you would just do a straight antiderivative, right? So it's possible that you get problems that are just, right off page 333, or maybe you can do a little bit of algebra to them. Now, here's one we're going to talk about in a minute. Actually, I've already helped some people. I think it was number 10. I think it might be number 10 on your thing. If I gave you this problem here, if I gave you this problem right here, what should you do on that? Split it up. Split it up. Now, you might be saying bring that up as a -1 distribute. I'd rather see you split it up. Anytime we have a single denominator, at least you should give a thought to splitting it up. Now, there are going to be times where it won't work, but here you should definitely split it up. So that would be x squared over x, and then that would be 1 over x, right? And then x squared over x is just x, plus 1 over x, and now you just do that antiderivative, away you go, right? So you always should be on the lookout for ones that, can I just do a basic antiderivative, or can I just do some algebra to it so that I can rearrange it and make it look right? So that should always be your first idea. Always should be your first idea. But on this one, we can't. We cannot distribute that through there. So we can't do it. Okay, so now you think U substitution. So what do you think you're going to pick for the U? Now let's start thinking a step ahead here. Because whenever we pick our U, which would be 1 plus x squared, so let's do it. The next step then is the du. I told you I was going to quit doing that du over dx thing, right? I'm going to skip that part. I'm just going to bring my dx over right away. What's the du? 2x dx. Don't forget that dx. You can't be leaving off the dx. You've got to have that in there. It's a critical part of the substitution. Okay? 2x dx. Now, here's what I would have been thinking through in my head. I would have looked at this problem and I said, oh, this is a great U substitution because I'll pick U to be 1 plus x squared. The derivative of 1 plus x squared is 2x dx. And look what I got sitting right there. I don't care about the 2. The 2 I don't care about. I care about it. It's going to be in the problem. But I don't care if there's a 2 setting there. I can deal with constants. I care that there's an x dx setting there, right? So when I pick U to be 1 plus x squared, I know the du is 2x dx, and I'm like, aha, there's an x dx sitting there. That's wonderful. That's what I want. Okay? So that's why I know this is going to work out well. So now we go to where we want to do our substitution. Okay? Well, let me do some circling. That's going to be U to the 1/2. Okay? That's going to be U to the 1/2. And then I've got this 2 and I've got this 4. Now the 4 I'll just pull out here in front. Okay, so that takes care of the 4. Okay, now I've got this x dx right here. Well, I don't want this 2. It's in the way, so I'm going to move it over. Whenever I got something that's not up there, that's kind of in the way, a constant, I just move it over. So now look what you got. You got x dx right there. Well, x dx is equal to what? 1/2 and a du. So I put the 1/2 and I put the du in there. So you can see how you deal with the 2 and the 4 and you just, those, but it's the x's that we got to take care of and the dx's that we got to take care of. We got to get out of it. So sure enough, I end up with a 2 sitting out here. And then what's the antiderivative of, right? Because now what is this saying? This is saying do the antiderivative of this with respect to u, which is what I want with respect to u. So raise that up to 3/2, so that'd be 2/3 u to the 3/2 plus c. Remember, the du just goes away because it's just there to say, all right, with respect to u. So the integral sign goes away because it's just telling me to do the antiderivative, so I've done it. So this becomes 4/3, and now in place of the u, I come back to my 1 plus x squared. to the 3 halves plus c. And I can certainly try this and check it out. Sure enough, if I bring this 3 halves down in front, the 3's would cancel. 4 divided by 2 is 2. So I would get 2. I would get 1 plus x squared to the 1/2. And then I would multiply by the derivative of the inside, which would be 2x. And sure enough, I would get 4x. And then the square root of that. And it works. Okay? But u substitution is all about turning this integral into something we can do the antiderivative. We can't do a product. We can't just do these individual antiderivatives. You can't just do that antiderivative and then do that antiderivative. It doesn't work. Plus, it would be something to the 1/2 with a 1 plus x squared in it. You can't do that. You can't just, there's no, antiderivative rules are on page 333. So, all right. Let's say that one. That's a definite integral. I don't want to do that one yet. Let's do this one right here. This was number 8, I think, in your book. It wasn't assigned. Let's talk about this one. Now, so that's your basic u substitution. I tell you what, before we do this one, are there some in your homework that you just really wanted to see? 33? What's that?
Root 1 plus 1 over x squared. Just the top is the square root. 1 plus 1 over x squared.
Okay, what's your question about this one?
I just
okay.
No, very good.
Now, I'm not going to finish this one because I think it's exactly what we did here. We let u be the 1 over x right here. And then our du, because that's x to negative 1, then our du became this 1 over x squared, which is setting right there. Isn't this going to be the same thing? What are you going to pick for the u? The inside of this. It's going to be 1 plus 1 over x, right? So, if you let the u be 1 plus 1 over x, or 1 plus x to the negative 1, what's the d? The 1 goes away, it's negative 1 x to the negative 2 dx. And sure enough, this will be down as an x squared, and isn't that setting right there? Right? So that whole thing is setting right there, so that's going to be just your negative du. This is going to be square root of u, so the whole thing is just going to be u to the 1/2, right? And you're just going to do that antiderivative. Does that make sense? Yeah. Okay, what's another one? 10? What was 10? X over 1 plus x. All right, so let's talk about this one. This will be a good one. This is going to be this is related to this right here. Remember when I said if you've got a single denominator, split it apart, right? Split it apart. Well, this one we can't do that, right? Because we don't have a single denominator. So you can't split denominators. We can't put this as x over 1 and x over x. Never split denominators. Single denominator, you can split your numerators. Quick example. 2/3 plus 4/3. We all know that is 6/3, right? That's 2 plus 4 over 3, right? You can split that apart, right? 2/3 plus 4/3 is 2 plus 4 over 3. That's 6/3. You can split that. Single denominator. Now switch that around. 3 over 2 plus, let's do 3 over 2 plus 4, right? We all know that is 3/6, 1/2. You cannot split that into 3 over 2 plus 3 over 4, right? That doesn't work, right? You cannot split a denominator, but you can split it this one, okay? So, single denominator, split it apart. So we can't split this one. So they said let u equal 1 plus x. Now, that doesn't seem to be the inside of anything, right? Now, so let's talk about that. So the first thing we look for is something on the inside, okay? So we got a u to be something on the inside. The other thing we look for is to let u be the bottom of something, especially if there's not a bunch of powers and stuff. So if we let u be the bottom, what's the du? 1 dx, right? So the derivative of that is 0, derivative of x is 1. dx, you can't forget this dx, right? This is du over dx equals 1. You bring the dx over. You can't forget that dx. It's a critical part of it. Okay, now when we sub this out, what do we end up with? Well, let me use some color here. So this ends up being u. The dx ends up being du. And we've got this extra x floating around up here. So this is something that we also need to make note of. What can we do when we have an extra x sitting there?
You rearrange the e.
Exactly. Now, I'll come back to something I said here at the beginning of the day. Oh no, I guess, yeah, I did. Right here, when I said, well, I think I said it, maybe I said it this morning, somebody was looking. When we're substituting making our new integral, we can use any of this stuff over here to make the substitution. Okay? So, right here, where am I at? Right here, we can subtract a 1 from both sides of this right here. Did you do that, actually? You did it. That's exactly what you want to do. Okay? So now we can, and this is where my circling comes in handy, because I replaced everything, but I haven't substituted out this x. But I now can, and I can put a u minus 1. Now you might look at that and think, well, that doesn't look much different than our original. Yeah, but it is, because it's got a single denominator, right? This has a single denominator. So now we can split that apart. So u over u is 1, 1 over u is that, and now we can do our antiderivative. Now this is also kind of interesting. Watch this. What's your antiderivative of 1? U. Minus, what's your antiderivative of 1 over u? ln u plus c. Now you put your 1 plus x back in, you get 1 plus x minus ln 1 plus x plus c. Right? Is that what you have then? Now watch this on my calculator. Let me do the integral. And I don't mind you using your calculator to check some of these. Okay, so what was the problem? It was x over 1 plus x dx. Now, first of all, your calculator doesn't put the plus c's in there, so they're always going to be missing. What else do you notice? The 1's missing. What happened to the 1? Well, it's related to the c. What is c? Just some arbitrary constant. What happens when you take some arbitrary constant and you add a 1 to it? It's still just some arbitrary constant. So for our purposes, this seems kind of weird. 1 plus c, c. 2 plus c, c. 2c, c. 2 times c is just some other arbitrary constant. So c. So I wouldn't count it wrong if you had that 1 there. But whenever that happens to us and we sub back in and we just have some constant and it's added to the c, let's just say that it gets absorbed into the c. That 1 plus that c is just c. And there you go. Okay? Now, if we were finding a specific c, that would make a difference, right? If we just got rid of the 1, then we went to find that c, it would be a different c than if you had the 1 there, right? Because it's got to come out to be the same. But, so don't worry about it in this one. Okay, so now let's go to this one, because this is very similar. This one very similar. This was number 8. This was number 8 in okay. So we've had our basic U substitutions where we pick a U and then the du is sitting right there and everything works out pretty nice. Now we've talked about where we have maybe some extra x's. So what do you think you're going to do with pick for u here? Let u be what? I'm going to pretend I didn't hear you. You're telling me you can do that? So square root of 9 minus 4, which would be square root of 5, that's the same as 1. Is that what you're telling me?
9 minus x squared 2.
No, not quite. You're getting closer.
It's 9x minus
9 what?
it's 9 minus x squared.
Yeah. The inside, not the whole thing, not to the 1/2 pattern, just the inside. Just let u be the inside. Yes, we cannot do the square root of 9 minus x squared and write that as 3 minus 7. That is no good. If we could, heck, that'd be great. If we could, then we would just distribute, then we wouldn't even do substitution. Okay, you guys go from there. You guys go from there and tell me when you run into a stumbling block. All right, what's happening? You got something extra? What do you got that's extra? X squared is extra. There's an x squared that's extra here. Okay? Because look what we get. We do our derivative, du, and that's negative 2x dx. The 3 I can just bring down. This would be square root of u, so we know that. So that's u to the 1/2. So I've got this x cubed sitting here, and I've got this dx. Over here, I don't want this negative 2, so I'm going to divide that over. Here I've got an x dx. Do I have an x dx up there? Sort of. Right? Okay. Isn't there an x dx? Oh, I froze it. Right here. Isn't x cubed the same as x squared times x? Right? So I've got an x dx right there. So that x dx would be negative 1/2 and a du. Now I'm going to leave myself a little space in because I know I'm going to need it. But you might not have noticed that, but then you can figure it out. See what I've done? So, and this is where the circling kind of comes in handy. So I took my x cubed and I rewrote it as x squared times x. And so now I got an x dx that's a negative 1/2 du. And I got this x squared left. Well, what's x squared equal to? It's u minus, well, I think it's 9 minus u. If I add the x squared over, I would get that. And then I subtract the u. So x squared would be 9 minus u. So remember what I said. You can substitute with any of this stuff here. So you can take any of this stuff here and rearrange it however you want, the u and the du, to be useful. So the x squared is going to come out, and a 9 minus u is going to go in its place. Now look at this. Now you might be saying, well, guys, that doesn't look that much easier than what we had before, but it really is, because what can you do with this? you can now distribute. See here, we couldn't distribute because the 9 minus x squared was inside of a power. Whenever you have something raised to a power, you can't distribute through that. What this did, by letting us pick this as a u, is it made that, the power, just be the single thing, u to the 1/2, and then we had this. Now we can distribute, and now you can just go to town. So this becomes -3/2 out here. This becomes 9u to the 1/2 minus u to the 3/2, okay, du, okay, and away you go. And then now you can rate. Now you got to raise it up. And it's going to get messy with fractions, but I don't want to spend a lot of time doing that right now because you guys can do that. And you can, right? You need to practice some of these on your own. Okay, it's one thing to sit there and watch me and follow along. Oh yeah, that makes sense. Oh yeah, I get it. Then you start doing it. Okay, all right. So let me talk about two other quick ones, real quick, right here. Let's do this one. Let's do this one. I want to show you something on the calculator with this one. So, matter of fact, this is very closely related to the last one. So you guys try this one. You guys go ahead and do this one real quick. Give me a few minutes here to get as far as you can. Will, what do you got?
I got 1 plus x squared minus 1 plus x.
That's a lot easier.
What'd you get, Matt?
I got like 2/5, 1 plus x to the 5/2 minus 2/3, 1 plus x to the 3/2. Plus.
Yes. Now, I know I may not give everybody ample time here, but 1 plus x is on the inside, so that's your best. You cannot distribute this x through here, so you can't do anything with that, so you let u equal 1 plus x. The derivative of u, du, is 1 dx. Don't forget that. It's always nice when du equals dx because you can just substitute them straight. But the downside when du is equal to dx is there's usually some extra stuffs hanging around. That's the problem. So right here, this ends up being u to the 1/2 right there, and this dx ends up being just du right there, but you've got this extra x hanging out here. So what do? You solve this for x. So x would equal u minus 1. So the x subs out and the u minus 1 goes in its place. Now we can distribute. So that was the beauty. You could not distribute here, but we can distribute here. So I don't know where. You got to have the square root there. Yeah. So now you get u to the 3/2 minus u to the 1/2. Notice I still have my integral sign because I haven't done the antiderivative yet. All I've done is substitute and distribute. So now I'm going to do my antiderivative. So I raise that up to 5/2, divide by 5/2, which is that. Raise that up to 3/2, divide by 3/2 is that. Put my 1 plus x back in. Now, let's talk about your calculators for a minute. So you're working at home. You're studying for the Gateway test. You want to check your answers, see how you're doing. So you go to your calculator and you check that answer, okay? And so I did it right here, and it gives me this, which looks nothing like what I just had, right? Now I showed you when we were doing the derivative test how you can do this. So you can do a solve. So if you come down here to this line here, okay, and then scroll over, you can see what I typed in. So what I did is I did a solve. So I did solve, and then I grabbed their answer and set it equal to my answer. So if you look here, on the right side of this equal sign is what Max just told us. And I did a solve of that equals that, and you should get true. Should say true. And that's telling you, whoops, that's telling you that this is equal to this all the time for all x. And so that's why it's a solve, but you're not, it's like solving 3x plus 2 equals 3x plus 2, right? 3x plus 2 is equal to 3x plus 2 for all values of x. They're equal. So when you get true, then that tells you what's. Now, there are some times through some limits on the calculator, limitations on the calculator, that you may not get that on some really kind of weird looking ones. It may not say that. It doesn't mean you're wrong. You look it up in the back of the book, it may not even be written quite the same way you did. So it can be a limitation, but it is one way you can use your calculator to check your answers. Okay, because there's going to be a lot of times where your answer is not maybe going to look like what the calculator says.
Why is the calculator different?
Well, it just has some rules for how it simplifies things and how it writes things. So it has some rules written in. So what it did is it factored out. If you look at what the calculator did, the calculator adds in, we put it in red. It took remember we talked about how you factor out the lowest power? So the calculator factored out a 2. Both of these have a 2 in it, right? So it factored out a 2 and a 1 plus x to the 3 halves. Now what would be left? Well, you'd have a 1/5 and a 1 plus x. 5 halves minus 3 halves is 2 halves, which is just 1. And then minus a 1/3. That's what it would have left, right? So then what the calculator did is it said, okay, let's distribute that. So this would be 1/5 plus 1/5 x minus 1/3. Let's get that into a common denominator of 15. So this would be 3/15. This would be 3/15 x, and this would be 5/15. Now what's 3/15 minus 5/15? Is -2. So this would be 3x over 15 minus 2 over 15, which the calculator would just write as 3x minus 2 over 15 multiplied by that. So it would just put it, since it's multiplied, it would put it all over 15. It'd bring in the 2, it'd bring in the x plus 1 to the 3 halves. So you got 2x plus 1 to the 3 halves times the 3x minus 2 all over 15. And if you look at what the calculator had, that's right. 2, x plus 1, 3 halves. So x plus 2 all over 15. So it factored it, it put it in a kind of factored form. Okay, I tried to expand. I used the expand command to tell it to expand this, but it didn't write like this. Again, it got common denominators. It's weird. So that's what the calculator was doing. Okay. All right. One last comment here, because I want to leave you some time to get to work here and ask me some questions as you need it. But here's one right here. So x over 1 plus x squared. Now, you've already seen this a little bit. When you see a 1 plus x squared down there on the bottom, doesn't that make you think of arctangent? It should make you think of arctangent. But in this problem, actually, it shouldn't make you think of arctangent. You got to understand the difference, right? If I would have given you 4 over 1 plus x squared dx, then that is arctangent. Okay? Because you can pull the 4 out in front, make that a 1, that is arctangent. Problem is you got this x here. So what should we do on this one? This is actually a u substitution. Remember I said let u be the inside, but if there isn't an inside, another good thing is let u be the bottom. But here's why you think that this is such a good thing. And think ahead now. If u is 1 plus x squared, what's du? 2x dx. Aha, there's an x dx setting right there. That's why it would not have been a good idea on this one. Because there isn't an x dx setting there. So we don't want it. We want to think of arctangent. But in this case, we want to do a u substitution. And so they're very similar looking problems, but you do them totally different. The one with a 4 up there is just an arctangent. The one with an X up there, something totally different. So now you move that 2 over there. And now you can substitute nicely. The bottom is just going to be U. The X dx is going to be a 1/2 and a du. So that just leaves you a 1 up there. And what's that antiderivative? That's ln. And then the other reason I wanted to do this one is I want to make a comment here about the bars. So this would be ln u plus c. So you put your other thing in here. ln 1 plus x squared plus c, like that. Now, guess what? If you go onto your calculator and you tell it to do the antiderivative of 1 over x dx, the calculator will put bars on there. Okay, ln x in bars. If you type in this problem right up here, it will not have bars on it. Why does there not need to be bars on it? Well, right here. No, not even because of up here. It's because of right here. Well, why do you need the bars? Because you can't have the inside of log be negative. The inside of log can't be negative, right? So if it's ln x, we can't let that x be negative, so we put bars. But what do you know about 1 plus x squared? That's always going to be positive. 1 plus x squared could be 0. It's the smallest x squared could be. And then you add a 1 to it. So this is always, so 1 plus x squared is always positive, so the bars are unnecessary. Leave them there is fine. They're just unnecessary. You don't need them. So if you did this one, your calculator would not put bars in. You might be wondering why you didn't put bars in. Okay. Well, because we don't need them. If this had been 1 plus x, then we would need them, right? Because 1 plus x could be negative. But 1 plus x squared can't. All right. So for tomorrow, let's do many more problems. Oh, I know, I skipped one. Okay, we got to go back to this one. Definite integral now. What do? Well, we do everything the same until we get down to the plus c part. Then we leave off the plus c and we do our right bracket. So, for this problem, I'm just going to ignore the 1 and the e for right now. And I'm just going to say, all right, what's my u? ln x. Why? Because it's on the inside, but now let's take it one step further. Not only because it's on the inside, when you do the derivative, you're going to get 1 over x dx, and 1 over x dx is setting right there. That's why you're going to want to pick that. So when we sub stuff out, what's this top end up being? U cubed. What's this bottom end up being? That's just the du, right? 1 over x, so this part here is u cubed, this part here is du. Now, we got to talk about this. So this is a very easy substitution problem, right? From this standpoint. Now, what we got 2 routes we can go here. I don't care which one you do. But you got to know about them both because on your homework they're going to ask you about it, number 1. And this is going to happen to you on the packets and the final and the AP test as well. One option we have, these numbers here are x values. This is x equals 1. Matter of fact, in the old days we used to write that a lot. We used to write x equals 1 and x equals e up there instead of just 1 and e. Those are x values. I have now changed this into u's. So one argument is we should now change these numbers to u's. It would be wrong to put a 1 and an e here. This is the area of this function from 1 to e. What we're saying when we write a new integral is that's the same area as this function from somewhere to somewhere. How would we change these to u's? Not multiply. It's not multiply. Plug them into L. So take E and put it in for X. What's ln E? 1. Put a 1 in for X. What's ln 1? 0. Now, we've got a new one. So on a couple of your homework problems, they're going to say, find the A and the B that makes this, and they go, and they write A, B, something U, DU, blah, blah, blah. Well, they're just saying, okay, when you make your new U integral, now do this. So now, when we do our antiderivative, our 1/4 U to the 4th, like this, we don't have to go back to x's. Because we've now got this 0 and this 1. Remember, when we do our right bracket, we don't put on the plus c, because it would just subtract out anyway. So now we can just put in our 1/4. We put in our 1, we put in our 0, and we get 1/4 times 1 minus 0, we just get 1/4. Does that make sense? Now the other option we have, and some people like this better, the other option we have is we didn't have to put those numbers on there. We could have went 1/4 U to the 4th, then we could have went 1/4 ln x, right? Like we normally do, right? Normally, once we get to here, we do the antiderivative, which is 1/4 U to the 4th. Then we normally go back to our x's, and then we put what numbers here? 1 and e. So now, when we put in, now we get 1/4 ln e to the 4th minus 1/4 ln 1 to the 4th. And what's ln e? That's 1. 1 to the 4th is 1, so that's 1/4. And then ln 1 is 0 times 0 is 0, so we get 1/4 minus 0, we get 1/4. You see, you get the same answer either way. So I don't care if you do the blue or the red, it doesn't matter to me. If this is the gateway test and you want to change these into new numbers, remember, it comes from here. So these are x numbers. You plug them into here, that gives you your u numbers. Then you can just do your antiderivative, do your right bracket, just do it. Or you can do what you're used to doing, which is go back to x's. But you're still going to end up doing the same thing. You're still going to end up plugging the e in there and the 1 in there, which you did up there too. So it's not really shorter one way or the other. But you should get the same answer. Okay? But they're going to be like multiple choice questions on the AP test where they want you have to figure out what would be the new limits, what would be the new u numbers. So you're going to have to know what that means. You're going to have to understand what they're talking about. All right, so let's do, let me see what I got here. So out of section 5.4 in the book, let's do 11 through 14. Those are some definite integrals, so the thing we just talked about. Probably, I'd say you should probably do about, about 7 more from number 23 through 74 in that section. There's 50 problems in there, right? You did 33, you did 43. You should pick about 7 more. And then LH, this is a new LH packet. Hang on to that other LH packet because you're going to need it. This LH packet. So if you look at your assignment sheet, okay, if you look at your assignment sheet, okay, it's that top line, LH 310's got like 7, 9, 16, 19, 24. No, it's not. Is it 24? No, they're not circle. I don't think they're circle. There are some circle ones, but it's not. Let me see here. I might skip a few here. Let's go. What did I put? 19, 24. 24. Let's do 37, 37 and 43. So that's quite a few. I mean, but at this point, it's all about practice. I mean, if you're gonna, and you guys have been through one gateway test, so you know I'm not lying, that if you're gonna get 8 out of 10 on these, you've got to practice and practice and practice, and you've got to, because you just start seeing the same things, some of the same things. You, oh yeah, I remember when I do this, if I let you be this, and this will happen, and this will be good. Okay, and they're not all use substitution. There might be some where you don't, where you can actually just do kind of a straight antiderivative or just simplify it or whatever, a little bit. So, okay, so let's do those right there.
Shoot it.
Yeah.